So just now I mentioned that we have finally obtained the equations for predicting the value of b and a based on the sum of square error, minimizations of the sum of square error. Well, the equation looks complicated, but the application is quite straightforward. If I can explain a little bit, okay, let's take this as an example, xi, summations of I equals to 1 to n. So summations of I equals to 1 to n represents the number of input data that you're given. Let's say if you're given 29 input x, so n will be 29, meaning that you take the summations of all the 29 input x that you have collected as your data. And then sum them all up, multiply with this term. This term represents the summations of all the respective response yi based on the collected x input data. So let's say you do a certain experiment. Okay, you collect 29 input data x. And based on this 29 input data x, you observe that they have 29 respective output data or output response y. So these two terms represents the summation of all the input x, and this represents the summations of all the output y. And then you sum them up and you multiply them together, as simple as this. And this term represents the multiplications of x and y in each of these I level. So x multiply y, then you sum with the x2 multiply y2, sum with the x3 multiply y3, and so on and so forth. Okay, so n, remember, represents the number of input data or number of observations that you have performed. So to calculate or to predict the calculations of b, you can either use this equation or this equation. And after you have obtained the value of b, then you can apply into here and find the value of a. And with this, you have obtained your regression line equation a and b, right? Just now we say y equals to a plus bx. And then there's one thing, okay? Remember that what we have said just now. Remember we said that the value of our a and b and also our regression line, they are predicted at best. We are only fitting the best as much as possible. And the level, how well we fit our line, okay, how well we obtain our regression line, if you can relate from these two equations, you will observe that I would say the quality of the fitting, yes, is based on your observation and based on your collected data x and y. So if you have obtained insufficient value of x, then the quality of the fitting will not be as good as what other people would have obtained if they collect more x or more experimental data. And also, it also depends on the accuracy of your collected data. So the amount of your collected data and the accuracy of your collected data influence the quality of your fitting line. Therefore, the A and the B value that you have predicted over here is not the true A and B value. Okay, same like what we have just mentioned just now. The regression line is the best fit. They are not the true regression line. So if we know that our line and our parameter A and B that we obtain is not the true values, then we know that there is definitely a true value, okay, that we do not know, as I mentioned just now, but we want to try to idealize and try to get that value. So let's call those true value alpha and beta, all right? Instead of A and B, we call it alpha and beta, okay? And instead of y hat over here, let's call our ideal regression line as mu, like this, okay? So what are these equation over here? This equation represents this equation gives us a way to calculate what is the actual value of beta around a certain interval, okay? Based on, for example, yeah, let's take the first line over here. Based on the b value that we have calculated and the t distribution, t over here, and this value s and ssx, which we will explain in the next slide later on, we can determine what is the upper limit of our